Hi all, welcome to my YouTube channel, Know About Embedded System. In today's video, we're going to discuss how to develop an embedded C program for I2C protocol with completely hands-on. And also I'll show you output in the end of this video. So before starting the video, if you are a new viewer to my channel, kindly subscribe my YouTube channel and gain the knowledge on embedded system. Let us start the video I2C programming here. So guys, in the previous video, we have already discussed what is I2C protocol, how it is designed, what is the frame structure, and many things we have discussed. And today's video, we will be discussing about I2C programming. And you know that this is a frame already. You can watch my video, the link in the description box. You can watch that video about the I2C. So coming to the interfacing diagram. So this is an interfacing diagram of your I2C protocol. So we will be having in one end, we'll be having a microcontroller, and this is your slave. So slave here, what I'm considering, it is a EEPROM slave it is. Here you can see the slave is a EEPROM memory, which is having a slave address of A0. Okay, so one side we have a microcontroller and that will be acting as I2C master, and one end I have I2C slave, which is of EEPROM memory, which is having a slave address of A0. And for this I2C port pins, here we have defined 0.27 is acting as a SDA and 0.28 is acting as a SCL. So these two port pins we are going to use in the programming. Okay, so now coming back to the slave here. So in the theory part, we have explained 5-bit slave address. So we have explained 5-bit slave address, but actually while developing the code, we have to send it 7 plus 1 bit. So you need to remember the frame here. So we'll be using a 7-bit slave address and followed by one read write bit. So both together we have to transmit in the frame. So that is why when you are talking about original slave address, that is 101 and 000, this is the original slave address. But when you combine with the read write bit, it will become like this. So when you combine with the read write bit 101 and 000, and this is your read write bit. So read write bit I'm making as 0, saying that master in a write mode. So master write mode I am transmitting. Okay, so 0 means master write and 1 means it's master read. So when you put together both 7 plus 1 bit, it will become 8 bit, and these 8 bits, these 8 bits will looks like this. So in this, original 7 bits are slave address, and the least significant bit is your read write. So both together it is going to be A0. So this is the slave configuration. We have to do it, and also we have to add on memory pointer that I'll explain in the coding part. Okay, this is a very simple interfacing diagram with respect to the I2C. Now let us go back to the user manual here. In the user manual, we have to understand some of the registers. 4 to 5 important registers are there that we have to understand. I'll just write it down what are those things. So we have to understand, one is I2C concept, then so this is I2 concept, then I2 con clear, and then I2C, I2 SCL, L, then SLH. I2 SCLH. So these 4 register we have to understand. What is this I2 concept? Very straightforward definition here. I2 concept means it is a control set register, and this is your control clear register, and these two are used to configure the I2C speed. These two registers are used to configure the I2C speed. How to do that, I'll tell you later in the next part. So this I2C concept is there. No? This is going to define different operations of your I2C protocol. Here you can see this is your I2C concept register, and this register is basically 32-bit register. Out of that, only 5 to 6 bits we are using, and rest all other bits are reserved here. Bit number 6, you can see this is a bit number 6 stands for I2C enable. Bit number 5 is a stop bit generation. Bit number 4 is a stop bit generation, and then bit number 2, you can see bit number 2 stands for assert acknowledgement, nothing but acknowledgement flag, and then we have interrupt flag here. Bit number 3 is an interrupt flag. The same interrupt flag we will also consider as acknowledgement flag. So both purpose we can use interrupt flag as an interrupt generation, and at the same time we can also consider it as an acknowledgement flag. Okay, so these are all the things with respect to concept. Bit number 65432. Same thing is available in the conclear as well. Here you can see this is my control clear register, and in the control clear register similar fields are available. Just if you scroll down here, you can see this is to clear. Con clear means control clear. If you want to clear operation of your asset acknowledgement, you can do that. If you want to clear interrupt flag, you can clear it. If you want to clear the start bit, you can use it. And if you want to disable the I2C interrupt, I2C peripheral, that also you can do. So this register for con clear. And finally, I want to go to the speed calculation. Yeah, so this is a formula they have given in the user manual. Every protocol will have its own small calculation part. Similar to that, here also we have. So we have formula like this. I2C speed is equal to peripheral clock divided by I2C SCLH and SCLL. So peripheral clock I'm considering 24 megahertz. This is what we have configured already, 24 megahertz, and these two parameters, what are those? I'm just configuring as 120 and 120. So 120 plus 120. So if you calculate the I2C bit frequency, it is going to generate 100 kilohertz. Okay, only this much you have to understand with respect to the register when you want to develop the coding part. Okay, so with this, let us go back to the coding. In the coding part, as usual, I have already done the basic skeleton part of the coding. Just we have to develop the main code. Yeah, here you can see 0.27 and 28 both are acting as SD and ACL line, and the slave address, as already told in the previous explanation. So we are going to use 8-bit slave address plus one read write, 7-bit slave address plus one read write bit. So altogether it is going to be 8-bit, and that slave address is 0xA0. This is the first point we have to remember. And then, so in order to select the pin functionalities, I have already defined the macros for pin function 0, 1, 2, 3, and then here you can see these are all I2C macros. Just now whatever I have discussed, same thing, I kept it in the form of macros. I2C enable, I2C start bit generation, I2C stop bit generation, I2C interrupt flag, and assert acknowledgement. Then totally 4 functions we're going to write. One is I2C configuration, start bit, stop bit, and data transfer bit. Data transfer function. 4 functions we're going to write it. So now let us start the first one, I2C configuration. Here you can see the line number 59 to 65 is the function what we supposed to write. So part of the code I have already written here. Line number 61. So this is to select the pin functions. Okay. So just I'll write one comment here. P 0.27 and 28, right? Yeah, 0.27 and P 0.28 will be acting as I2C, SDA and SCL. I'm just configuring as SD and SCL. You can just refer my previous video. I'll put the link in the description box. Okay, so how to do that you can watch it. Then just now this is a formula to calculate the I2C speed, and similar to that SCLL and SCLH, just now I have shown the calculation 120 and 120 I'm uploading here. When you do that, it is going to take it 100 kilohertz speed. Okay, then finally I have to enable I2C by using I2 concept. So I2C concept, I'll be enabling I2C and I'll be giving a assert acknowledgement. Here you can see if you want to enable macro, I have already defined bit number 6. Just you can put it here. So this is going to enable the I2C, and if you want to assert acknowledgement, or if you want to give an acknowledgement, and if you want to send an acknowledgement, receive an acknowledgement, then we have to enable this bit, assert acknowledgement. So this is your second part of the configuration. Okay, so totally we have 4 lines of code: pin function selection, and then operating speed. Then we're going to enable the I2C and asset acknowledgement. This is my first function. Now the second function we have to generate the start condition. To generate the start condition, some 2 to 3 steps we have to follow. The first step is we have to clear I2C interrupt flag, generate start bit, then wait I2C inter flag to set it, and then clear I2C interrupt flag, and then clear the start bit. So 5 steps we have to follow. Okay, so how to clear I2C interrupt flag? So you know that already. We have two different registers for controlling the operation, conset and conclear. Now I'm going to use conclear. I2 conclear is a register which is used to clear the control bits. Okay, then so this is the bit number 3 we're going to use to clear. So is equal to, just you can write it as conclear here like this. Okay, so this is going to clear the I2C interrupt flag, and then if you want to generate the start bit, use same concept which we have used previously. Now this time I have to use a start bit generation. So start bit is nothing but bit number 5 here. Just you can give the start bit here. Okay. So now what it will do, this is going to generate the start bit. And after that, I need to check the condition here. So while negation, so use concept. I have to wait for flag to set. So nothing but this register I have to use I2C concept and perform AND operation, and I need to monitor for interrupt flag here, and then put it in a while of 1. So this is going to monitor, this statement will monitor your I2C operation. Once I2C operation is done, this flag will set, and then you can go for next step. Okay, after that I need to clear that interrupt flag, nothing but the same thing what we have used already. Just you clear it, and then I have to clear even I have to clear the start bit as well. Okay, so if you want to, just you have to copy this. So this is your second function to generate the start condition. Okay, so we have done I2C configuration here, and then we done with the I2C start condition as well. So 2 functions are done. Now third function we will move on. Third function is I2C data transfer. If you want to transfer data, 3 steps we have to follow. First, you have to load the data to the I2C buffer register. Then again wait for I2C interrupt flag to set it, and then clear the flag. So this process you have to repeat. In order to load the data, we have dedicated I2C data register is there, that is called as I2C I2 DAT it is. The name of the register is called as I2 DAT, and here the data whatever you want to transmit, that you can transmit from the main code. This is just a variable here. Okay, and then as usual we have to wait flag to set. Okay, just you copy here, paste it, and after waiting you need to clear it again. I2C interrupt flag. This process you have to, similar process we have to follow what we did in the previous code. Okay, so now what happened? So data is loaded to I2C data register. I2C will transmit, and once the transmission is done, it is going to update in the flag, and then we have to clear that flag. Okay, so now finally, so we have to generate the stop condition. If you want to generate the stop condition, again we have to use I2 concept, and this time I'll be using a stop bit here. Okay, so this is my stop bit generation function. So totally 4 functions we have written. So watch the video if you're not understanding once again. Okay, so this is the 4th function, and already prototypes already have declared I2C configuration start bit, stop bit, and all. Now coming to the main code. So main code, I'm just doing a basic clock configuration. I2C configuration function I'm calling here, and then I'm generating a start bit here. Okay, these 3 steps I'm doing here. Now the 4th step, what I have to do, I have to send a slave address. After starting the start bit generation, we have to send the slave address. So how do you send the slave address? You know that already. So slave address, you know what value we have to send it, that is 0xA0. Okay, this is my slave address. I'll be transmitting via function call. Then after that I have to send a memory pointer, because since my memory I'm going to EEPROM I'm going to interface, I have to send it some address I need to send, that is memory pointer, that should start from 00. Okay, so that's why I'll be sending second data as a memory pointer here. That memory pointer will be 00. Okay, then the third, actually I'm going to send a data. So from here onwards, whatever I'm transmitting, that will be your data. Okay, so first I'll transmit character A. I'll transmit four characters: character A, character B, and character C. Character C and character C and character D. Four character I'll transmit in the ASCII value. This is my B, this is my C, and this is my D. Okay, so four character I'm transmitting. After that, I'll just stopping the communication. Okay, so this is a complete code of your I2C. I'll just give you one glimpse here. So we have written four functions: I2C configuration, I2C start bit generation, then I2C data transmission, and then finally I2C stop bit generation. Four functions we have written here. Respective macros already defined, respective functions already defined, and then in the main program just I'm going to call my functions. So clock configuration, I2C configuration, start bit generation. So slave address, okay, here there should be 00. Sorry, yeah, so this should be 00. Then I'm transmitting data A, B, C, D, and finally I'm stopping the communication. So this is how we have to write the code in the I2C for I2C program, I2C interfacing. Now I'll just compile. We will check for errors. So there is no error here. So let us go to the I2C interfacing into the debug environment, and then we'll check the output. Okay, yeah, this is your I2C peripheral, and just for easy understanding, I'll put one breakpointer here. Okay, it will execute, your compiler will your software will execute until stop bit generation. Okay, then you can open your pin connect block. Okay, just you run it once before. Okay, just you run once and check here whether 0.27, here you can see 0.27 and 28, both 0.27 and 28 both are configured as your I2C port pins, right? So that is fine now. Now coming to the programming I2C interface side, here you can see, so this clock values, okay, clock divider values, these two 78 hexadecimal, nothing but 120 in decimal. If you want, you can just calculate this 78 in hexadecimal equivalent to our 120 in the decimal. So that both will result the master clock speed of 100 kilohertz. This is what you're seeing here. And finally, other part you can see here, we have enabled I2C, we have asset acknowledgement enabled, and many parameters are there. You can explore if you want more. Okay. Now here you can see this is your I2C communication, and this is your this part, whatever you're seeing, this is your actual data transmission mode. So mode talks about master in a transmission mode, or you can say master write mode. Okay, we made a RW bit as 0, that is why it is configured as a master write mode or a master transmit mode. So this is the first point you should know. The second point is slave address. I already told you what is the slave address. Basically the slave address is 50, and including rewrite it will become A0. Okay, so here it is showing original slave address, that is as 50, and this is your actual data what we transmitted. So if you look into the code here, so this is your code, and yeah, so if you look into the code here, the first actual data is the slave transmission, slave address, that is already done. The second data what I am transmitting, that is a memory pointer. That memory pointer also it is transmitting as 0 here. So this is 0 and followed by your 41, 42, 43. The 41 is nothing but the hexadecimal value for your uppercase A. Okay, so 41, then 42, then 43, then we have 44. These two are nothing but the ASCII value for A, B, and C and D. So these are all your actual values for your ABCD. Okay, these are all the ASCII value for ABCD. Okay, so in this way, using I2C protocol, you're able to transmit from master to slave and slave to master as well. So currently I'm showing only one way. In a similar way, you can do the programming for in a reverse order as well, slave to master. Okay, I hope this video is informative. Please click on like button and subscribe to my YouTube channel and gain the knowledge on embedded system. Let us meet in the next video.